Good day. We are the Group 4 of STEM Float 1, and this is how we perform Mission Impossible. Starting off with part 1. It is shown here the different roles that were assigned to each member of the group. For part 2, construction of the device.
The prototype to be used in this project will be a parachute because air resistance overwhelms gravity's downward force. The net force and the acceleration on the falling biological weapon are upward, and an upward force on a downward falling object would cause that object to slow down. The biological weapon thus slows down. The manila paper will represent the canopy since it allows air to enter into the paper. The conditions inside the canopy help shape the paper parachute and increase the drag, creating more resistance and further reducing the descent speed. While the yarn serves as the suspension lines because it connects the canopy to the load, it forms a net or skeleton for the canopy. This skeleton absorbs much of the parachute's opening shock. A box made of manila paper would be the load since it is where we will store the biological weapon represented by an egg.
Isaac Newton's second law of motion is the basic principle seen in this egg drop experiment. It states that when a free-falling body accelerates, its velocity increases, and as the velocity increases, the resistance of the air to the object's motion also increases. When the upward force of air resistance balances or equals the downward gravitational force, the object's net force is zero. The object continues to move downward with a constant speed called terminal speed or terminal velocity. Our goal in this experiment was to create more wind resistance to slow down the object's speed, not to brake when released from three heights, 1 meter, 2 meters, and the second floor. The wide surface of the canopy absorbs the air and slows down the paper parachute.
Materials. The materials needed for this activity are 1 meter masking tape, 1 meter yarn, 1/2 manila paper, and an egg. Manila paper is a versatile material in this project. It was used as a canopy for the parachute and as a load. The strings attached to the canopy and gravity pull the parachute to the ground. Without the strings and manila paper, there will be no air resistance created. The tape was used to stick the string and the paper together. The egg will represent as a biological hazard in this experiment.
In building our prototype, the first thing we did was to gather the materials needed. Then, we cut out a 5 by 5 cm from a 1/2 manila paper that will be made into a box to serve as the load. The next thing we did was to fold a 30 by 30 cm manila paper into a cone shape that will be used as the canopy. After doing so, we measured the yarn and equally cut it into 4 and taped it into the canopy. Lastly, we used the remaining paper as a cushion for the egg and used the remaining masking tape to prevent it from rolling upon the parachute's land.
The strength of gravity pulls us all to the earth uniformly. Whether it is a stone or a feather, no matter what the object is, it will have an acceleration of 9.8 meter per second squared downward to the earth. A way of understanding how a parachute works is to realize that it dramatically lowers the object's terminal velocity by increasing the air resistance as it falls. It does that by opening out and creating a large surface area of material with a huge amount of drag. Parachutes are designed to reduce a person or an object's terminal velocity by about 90%. So it hits the ground at a relatively low speed of maybe 5 to 6 meters per second, roughly 20 km per hour or 12 miles per hour. Because gravity's natural effect is reduced, the force is reduced when the egg hits the ground.
When the paper parachute was dropped 1 meter from the ground, we can see that the egg did not break. The same with the second trial. When it was dropped 2 meters above the ground, on the final trial, the egg was dropped from the second floor and didn't break when it hit the ground. There was no disaster since all the trials were successfully